This is the solution to question 7. We have a particle falling vertically down onto a plane that's inclined at an angle of 45 degrees. So that's a surface there, 45-degree angle there, particle falling down. Coefficient of restitution is a half, and falls down when it hits the plane. It's got a speed of 25 meters per second. So what I did is I got an angle here by drawing a cross at the point where the particle hits the plane. These two angles are alternate angles, and then these two angles can be worked out as being opposite angles. So they're both equal to 45 degrees. And the way to do this is we want to rotate the plane. So we rotate our point of view. We basically just twist the page so that we get something like that, where the plane now is horizontal and it looks like the particle is coming in at an angle. Once we have that, then we can write this initial velocity vector in terms of I and j. So I rotate the plane through 45 degrees clockwise, so as the clock turns, and my system becomes a little bit more manageable. So then it becomes a system that we can deal with. So there's an angle here of 45 degrees, a velocity of 20, or a speed even of 25 meters per second, and it'll rebound off. And the question asks us what is the speed afterwards and what's the angle. So we're looking for the velocity vector afterwards. We get the speed from that and the angle from that. Okay, so this thing has two components. It has a j component, it has an I component. And what we'll do is we'll use cos and sine to get the two components. So I've done that here. The horizontal component is going to the left, so it's negative. It's 25 by the cos of 45. Cos of 45 is 1 over root 2, which is why I get minus 25 over root 2. And then it's going downwards as well, hence the minus, and 25 by sine 45 is 25 over root 2. That's in the j direction. All right, go back to our diagram. And what we know now is when the particle hits the plane, it experiences an impulse perpendicular to the plane, so vertically up. So that means the j component of this is going to change, but the I component stays the same. So we apply Newton's elastic law in the j direction. So the j component changes, E is minus v over u. Rearrange it to get the j velocity afterwards is minus E times the j velocity before it collides off the ground. So it's minus a half for the coefficient of restitution, and we put in the j component in there. That gives me that then for the velocity in the j direction, and that goes in here. Remember that the velocity in the I direction stays the same. Okay, so that's my velocity vector after it collides or after it impacts off the surface. That's that velocity vector there. And now what we need to do is get the magnitude of it. So you know it's just the I component, or the number in front of the I component squared, plus the number in front of the j component squared under the square root for that. And the angle then is the inverse tan of the j over the I. And it's the 12.5 over root 2 divided by 25 over root 2, which is just a half. And the angle works out around 22 degrees relative to the plane. What I mean by that is that angle is around 22 degrees. And we don't bother transforming it or translating or rotating the plane back like so, because it's just a little bit too complicated. But if you did, that's a 45 degree angle. The particle comes out at a 25 degree or 22 degree angle to the plane. So it'll come out something like that, where that angle there is 22 degrees. So what you could do then is you could calculate that angle there as 23, and that would allow you to describe the direction accurately. But in these questions, it's typically not done. The 22 degrees relative to the plane is enough of a description. Okay, the final thing then is the impulse. So we have the velocity before, we have the velocity afterwards. So if we use mv minus mu, here we go, mv minus mu, we end up with 37.5 over root 2 kilogram meters per second. And just be aware of that impulse is perpendicular to the plane. It's like that. So when the particle comes down and comes out at the angle there, it experiences an impulse like that. And that's not in an I or a j direction, which is why we needed to rotate the plane so that it experienced an impulse in just the vertical direction, the I direction, and then we could apply Newton's elastic law in one plane only and not in two planes, because that's going to be a nightmare to deal with.